In the first part of this unit, we learned about Le Chatelier's principle and just basic stuff about equilibrium. Well, now we're going to apply that to acids and bases and titrations. We reviewed acids and bases earlier in the year, so let's just do a quick review of characteristics of acids and bases. Acids are sour tasting while bases are bitter. Acids generate or create hydrogen ions or protons. They donate protons to another substance, and they can accept an electron pair if they're Lewis acids. Bases, they feel slippery. These usually generate hydroxide ions, OH. When dissolved in water, they can accept protons. That makes them a Bronsted-Lowry base, and they donate electron pairs with Lewis bases. And we'll review again the three models just a little bit, but the Arrhenius model is simply, if you have H's, you're an acid. OH's, you're a base. And then the Bronsted-Lowry bases and acids are a little different. You're either donating protons or accepting them, and that includes more bases like NH3 ammonia. NH3 is a base. It's not producing hydroxide ions, but it's accepting a proton. And then you get into the Lewis acids and bases, which is all about electrons. And just remember that water, well, it can be either an acid or a base. It can either gain protons to form the H3O plus ion hydronium. Remember, H3O plus is hydronium. A lot of students will see hydronium and think hydroxide, so you have to be really careful in your reading. Hydronium, hydroxide, two very different things. Water can also donate a proton to become a hydroxide ion. We call that amphiprotic or amphoteric. Different words, means the same thing. And just remember that if you're going to transfer a proton, somebody has to be transferring and somebody has to be accepting. So there's always two things going on. And let's review the term conjugate acid-base pair. On the reactant side, you have your acid and your base. On the product side, you have the conjugate acid and base. So you're always going to have an acid, you're always going to have a base, and the acid goes with the conjugate base. So let's take a look here. Acids are always donating the H, the bases are accepting. So we're going to call HA some acid, and A negative is the conjugate acid-base pair. Now, I don't know if you can see that very well here. Get my pen to work. So HA is the acid. Over here, it lost the H to become the base. Acid conjugate base pair. And likewise, you've got water acting as the base. Well, a base is going to accept a hydrogen. So we call this the base, and this is its conjugate acid. So every acid has a conjugate base, every base has a conjugate acid. So go ahead and pause the video and do a little test. Can you look at this equation and figure out initially which is the acid and which is the base, and on the other side which is the acid and which is the base? And it really is easiest if you think about, well, who's donating the hydrogen and who's accepting it? Got my Wyoming coffee mug going this morning. So let's discuss the relative strengths of acids and bases. The more easily a substance gives up a proton, the less easily its conjugate base can accept a proton. So let's just think about the strong acids. HCl, we know, loves to give away an H. Well, its conjugate base is a Cl. Because hydrochloric acid loves to get rid of the proton, that chlorine is not going to be very likely to accept a proton. So they're opposites. The more easily a base accepts a proton, the less easily its conjugate acid can give it up. So if you have a strong acid, its conjugate base is going to be negligible, and that's what you see in this diagram. If you have a strong base, its conjugate acid is going to be negligible. In other words, it's not going to behave much like an acid. And then the weak are just kind of there in the middle. So the stronger an acid, the weaker its conjugate base. The stronger a base, the weaker its conjugate acid. So just one more time, let's reiterate what we mean by strong acid, weak acid, and negligible. Strong acids completely break down. They totally transfer their protons to water or a base or whatever they're with. and their conjugate base is negligible. It's not very likely that conjugate base is going to accept a proton. Weak acid simply means that it only partially dissociates. It only partially breaks down. And as you recall, that means we have fun math. We have equilibrium math we have to do. And so what you have with weak acid, say acetic acid vinegar, is a little bit of it'll break down into hydrogen ions and acetate ions, but a large part of it remains as acetic acid. It just doesn't break down. And by the way, the conjugate base, the acetate ion, is slightly able to take on protons. Negligible just means it's really not going to demonstrate any acidic behaviors at all, but its conjugate base is going to be pretty strong and can act like a base. So in much of this unit, we are looking at equilibrium, which means we're dealing with weak acids and weak bases. So you know you've got a reversible reaction. And so the question becomes, well, which is more favorable, the forward or the reverse? Well, in order to answer this, you really need to consider which is stronger, the base or the conjugate base. So if the base is stronger, then the base accepts hydrogen ions from the acid and the equilibrium lies to the right. In other words, the reaction is going to go forward. And this occurs when you have a strong acid. Remember, if you have a strong acid, we don't use the equilibrium arrow. We just use a straight arrow going, yep, it goes to completion. But if the conjugate base is stronger, then the conjugate base is more likely to accept hydrogen ions from the conjugate acid. And that equilibrium is then going to go to the left. And this occurs when the acid is weak, like vinegar. An equilibrium favors the transfer of the proton from the stronger acid to the stronger base to form the weaker acid and the weaker base. So there are a couple of questions on this on the homework assignment, and you're going to have to actually look at it and consider, well, which base is stronger, the base to begin with or the conjugate base? And that's where a couple of slides ago, that picture really comes in handy, the one that says, strong, weak, negligible, and that is in the textbook. Well, as you know, water can be both an acid and a base. We call this the auto-ionization of water. In other words, it will, on its own, break down into ions. Not a lot, but a little bit. So what are we talking about here? We're talking about you have two water molecules. One is going to act like the acid, one's going to act like the base. And you can see in that equation that one's going to become a hydroxide ion and the other one hydronium. So we can write a K equation for this, and it's Kw equals the hydronium ion, or H ion, times the hydroxide ion. We don't include the two waters because they're liquids. They're constants. We don't use them. And the water, by the way, just stands for ionization of water. Well, at 25 degrees Celsius, we know that the Kw value is 1 times 10 to the negative 14th. And this is a great little tool to help you bounce back and forth between hydrogen ion concentration, hydroxide concentration, and letting you find pH and pOH. So remember that when the concentration of H equals the concentration of OH, you have a neutral solution. Why do we have a pH scale? Well, would you rather deal with numbers like 1 times 10 to the negative 3 or 3? Okay, that one's not that bad. How about 1.56 times 10 to the negative 9th? Who wants to deal with that? So the pH is just a way of making the numbers make a little bit more sense. And that is the equation. We've used it in the past. pH and the pOH, they're exactly the same equation. It's just for one, you put in hydrogen ions, and the other one hydroxide. Just recall that acids have pHs of less than 7, neutral is 7, and bases are greater than 7. Typically, the scale goes 1 to 14, but I've seen negative values, and I've also seen values higher than 14. But again, 7 is neutral, less than that is acidic, greater than that is basic. So be careful. I know in my mind when I hear, oh, the pH increased, in my mind, for some reason, I think, oh, that means it's becoming more acidic. No, it's going up. It's becoming more basic. So don't let that one get you. Now, pH and sig figs is a little interesting. It's a little different. And I know in the past I said we always use 2 decimal places for pH, but I was mistaken. After my qualitative analysis class, I learned that finding sig figs for pH is a little bit different. And I don't want to get into all the math and whatnot, and it has to do with logarithms and everything, so just take my word for it. But what you do is you look at the original problem and figure out how many sig figs you would normally have. That is how many decimal places you take your pH to. So if your problem has three sig figs, your pH will go to 3 places. Kind of interesting. But as the hydrogen ion concentration increases, the pH decreases. I mentioned that. So we can use these equations to bounce back and forth between the ions, between pH and pOH, and just remember that pH plus pOH equals 14. And there's 2 ways we can measure pH. We can use a meter, which actually gives us a value, or we can use an indicator, which lets us know when we've reached the end point, which also gives us an idea of roughly where we are in the pH range, because each indicator changes color at a different pH. This is just a quick review of what strong acids are and what they mean. Strong does not refer to pH. Strong just simply refers to the fact that they dissociate or break down completely. Those are the strong acids you need to memorize. 3 of them come from column 17, HCl, HBr, HI. Then you have nitric, chloric, perchloric, and sulfuric. Now, not all resources agree that chloric, HClO3, is a strong acid. Your book says it is, we'll go with it. When you have a strong acid, we use the single arrow, not the equilibrium arrow. That implies that it goes to completion. So when HCl breaks down, you get hydrogen ions and you get chlorine ions. And the beauty in that is whatever the molarity of HCl is your molarity of the H. So if you have 6 molar HCl, I have dogs barking. You have 6 molar H, you have 6 molar Cl. So there's another example there. If you've got 0.2 molar nitric acid, you get 0.2 hydrogen and 0.2 of the nitrate ion. Diprotic acids are a little bit more difficult. We like to think that if you have sulfuric acid, 12 molar, you really get 24 molar. Not exactly the case. We won't stress on it too much, though. All right, let's talk about the strong bases. Again, these are bases that break down completely in water. Here's how you know the strong bases. They are OH with an alkali metal. So if it's in column 1 with an OH, it's strong. KOH, LiOH, etc. If it's an alkaline earth metal with OH, it is a strong base. Now, just FYI, LiOH, rubidium hydroxide, cesium, they're not very common. And when you get into the calcium, strontium, and barium hydroxides, while they're strong, they're not very soluble. So what does break down completely. It's kind of muddled, kind of icky. But just know that bases react with water to make OH. This is an interesting one, and you're going to see this on the homework assignment. One of the most common bases is something that has the O2 negative ion. For example, sodium oxide or calcium oxide will become ions in water to form sodium ions, calcium ions, and the O2 negative ion. Those O2 ions can then react with water to make OH negative. And for every 1 oxide ion, you get 2 hydroxides. Something to think about. While strong acids and strong bases are fun to play with in the laboratory, they're kind of boring when it comes to math. But weak acids and weak bases, yay, we get to have fun math. Yeah, I rolled my eyes. Weak acids only partially dissociate, so we have to use the equilibrium constant. And you guys know that we don't include solids and liquids, so for that particular reaction, we can write the Ka expression as it's written on the slide. I'm not going to waste time reading that to you. Just know that Ka is the acid dissociation constant. For acids that have carbons, hydrogens, and oxygens, it is the hydrogens that are bonded to the oxygens that are acidic, not the ones attached to the carbons. And I'll show you a picture of this somewhere on down the road. The larger the Ka value, the stronger the acid. The smaller, the weaker. So if you've got Ka 1.6 times 10 to the 10th, yeah, it's strong. If you have it to the negative exponent, weak. We will practice plenty of these in the classroom, so I'm not going to waste time on actually practicing one. But calculating Ka from pH is pretty similar to the math you've already done in the Le Chatelier part of this unit. But here are the steps you want to follow. Write your constant expression. So have that balanced equation. Write your Ka equals products over reactants. Make sure all your exponents are correct. Find the values you need to put into the expression. And remember, K means you have to use equilibrium concentrations. Once you you can use pH to find H or vice versa. In some of these, you're going to take the pH to find the H. Well, most of the time, your H and your OH are the same value. Think about acetic acid. It's going to break down to form H's and acetate ions. So those two are going to be the same. And you can find the acid at equilibrium. All you have to do is take the original value and subtract off however much it breaks down. So we'll practice these in the classroom, but just remember, you start with this acid, HA, and it's going to make some H's and some A negatives, not that many. And the mistake most students make is when they do the equilibrium math down below, they want to put the original molarity of the acid in there. It's the original molarity minus the concentration of H. So percent ionization is kind of along the same lines of what we were just discussing. It's the concentration of the ionized acid divided by the original times 100. The stronger the acid, the greater the percent ionization. And the concentration of acid that ionizes is equal to the H that forms. So you can also write it as the concentration of the H ions at equilibrium divided by the original times 100%. You do need to know how to do this. It also comes in handy for evaluating whether or not you should have used the quadratic formula. Typically, if you're doing a problem and you find the percent ionization and you're at 5% or less, then you don't need to use the quadratic formula. But if your percent ionization is greater than that, then you do. I usually go with the rule of look at your Ka value. If it's times 10 to the negative fifth or negative sixth or negative seventh or negative eighth, so on, you don't need to use the quadratic formula. But 10 to the negative fourth, negative 3, negative 2, negative 1, you do. And we will do it a couple of times. And then after that, we're going to cheat and say, we should use the quadratic formula. But we're not. We're going to get a lot of practice of taking pH from Ka. So you might want to pause this slide and write down the steps to finding this. Basically, what we're going to start with is writing the ionization equilibrium equation. Write the Ka expression correctly. You're going to be given Ka, so you can set that whole thing equal to Ka. And then where it gets a little tricky, and by the way, ice tables really make a difference on this one, is that for a monoprotic HA acid, so it just has one H, the H is going to equal to A. Because if you have HA, it's always going to break into H and A. So they'll be the same value. And what that allows you to do is a little bit easier math. The ice tables really make a difference. And then all of your equilibrium values are probably going to have an X in it. And so you're going to have the Ka value equals your expression with some X's in there, and you just solve for X. You may or may not need to use the quadratic formula. But again, we're going to practice this in detail. I've already mentioned this. Is it safe to assume there's going to be a time and a place where we can ignore those X's? Now, if you have X for H and your A negative is, I don't know, like 0.1 minus X, there's a time and a place where we can ignore that minus X. And we'll talk about that as we work through our problems. And it goes back to well, how small is the Ka value? If Ka is really small, times 10 to the negative fifth or negative sixth and so on, when you get X, it's such a small value that 0.1 minus that value doesn't really change the 0.1. So we can ignore the X's on occasion. Now, you may in college wind up with a professor like my son did, who he didn't care. You did the quadratic formula every single time, and he made you carry it to enough decimal places that if you didn't do the quadratic formula, you got the wrong answer. So just know that there is a time and a place where we can ignore some things because the values are going to be super small, and we'll work through that in our problem sets. Well, so far we've only been talking about monoprotic acids with just one H. What if you have more than one? Well, even if you have just H2SO3, it can ionize twice. And if you look at the first equation, well, it loses an H to form an H plus and an HSO3 negative, and it's got its own Ka value. Can't that HSO3 lose an H? Yes, it can. And so there's another ionization equation, and notice that Ka value is much, much smaller. In other words, H2SO3 is more likely to lose one hydrogen, but it takes a lot more to lose that second one. And you'll notice that if there's, like, citric acid has 3 H's, each successive Ka value becomes smaller and smaller. So very likely to lose that first H, not so much for the second one, and even less for the third. I'm not going to read everything on this slide, but I just want you to know that everything we mentioned for weak acids is the same for weak bases. So Kb is just the base dissociation constant, and if it's weak, again, it doesn't break down all the way. All the same rules apply. And just know that we have 2 categories of weak bases: neutral substances that have an atom with a non-binding pair of electrons like NH3 or other amines. Those are organic compounds that have an NH2 group on it. They are weak bases. And then the anions of weak acids also create weak bases. This also should be review for you. You should recall that Kw, that's the ionization of water constant, 1.0 times 10 to the negative 14th, is equal to Ka times Kb for a conjugate acid-base pair. So as Ka increases, Kb is going to decrease so that we always get the same value. And don't forget that pKa and pKb equals pKw, which equals 14. So this is just another great way to bounce back and forth between acids, bases, pH, pOH, all that stuff. So we know that acids and bases react together to make water and a salt. Well, we know those salts break down completely. So what we have is a salt solution. What we need to now consider is, do those ions from the salt further react with water to change the pH? So we're going to have to analyze the cations, the anions, and then the cations and anions together. All right, this is where it gets a little convoluted, a little muddled, a little icky. We need to talk about salt solutions. So just because you've got a weak acid and it breaks down, you think you know the pH, but it's not always that clear cut. And to be honest with you, we really should get into things like activity coefficients and looking at ionic strength of solutions and whatnot. We're not going to go that far in depth, but here's what you need to know. If you have an anion, the question is it going to further react with water to make OH and change the pH of the solution? Well, we have to analyze that anion. And so what we need to do is figure out, well, just how strong is it? So the first thing you should do is take that anion and put an H on it. If that becomes one of the 7 strong acids, we know that conjugate base is very weak. We know that it's not going to produce OH negatives from water. It's not going to affect the pH of the solution. The anion really is just a spectator ion. But if you put an H onto that anion and it's not a strong acid, then we know we have a weak acid, and therefore that anion is a weak base. And weak bases will react to a small extent with the water to make OH negative ions. That will increase the pH, making it basic. So you think you're at the end, you think you figured out what the pH of the solution is. Not necessarily. If the salts containing anions of ionizable protons like HSO3 negative, well, they're amphiprotic. So you need to know that those can go either way. They might react basically, they might react acidically. Well, how they behave depends upon the magnitudes of Ka and Kb. So now you need to analyze those 2 values. If Ka is greater, it's going to become acidic. But if Kb is greater, it's going to become basic. So the point is, you have to do a little bit more detective work to figure things out. Well, not only can the anion actually affect the ending pH, cations can as well. So you really have to look at what cations are in solution, and are they going to react with water? Are they going to change the pH? Polyatomic cations like the ammonium ion can donate a proton to water to make hydronium. This will decrease the pH. It will make it more acidic. Metal ions can react with water to decrease the pH. For example, iron 2+, zinc, nickel 2+, they can all react with water to create an acid. The larger the charge on the metal ion, the stronger the interaction between it and the oxygen of its hydrating water molecules. So, what have we learned? That sometimes anions are going to continue to react, sometimes cations will continue to react, changing the actual pH from what we thought. So let's make it more complicated. You have anions that might be reacting with water. You have cations that might be reacting with water. All right, so how are we going to know whether a salt forms an acidic, basic, or neutral solution? Well, if both the cation and anions of the salt do not react with water, well, we'll expect the pH to remain neutral. And this salt has the following characteristics: an anion of a strong acid, like Cl negative, and a cation from group 1A or the heavier members of 2A. If an anion reacts with water but not the cation, the pH is going to be basic. And this would be an anion of a conjugate base of a weak acid. And the cation has to be from group 1A or the heavier members of group 2A, like calcium, strontium, and barium. If the cation reacts with water and an anion doesn't, well, obviously it's going to be acidic. And for this, you would have the cation of conjugate acid of a weak base or a small cation with a charge of 2+ or greater. If both the anion and the cation both are capable of reacting with water, the acidity level depends upon the relative abilities of those ions to react with water. So it's not necessarily clear-cut, but a little detective work and we can figure it out. So we need to think about chemical structure and how that affects acid-base behavior. So first, if molecules contain H, they will act like a proton donor. They will get rid of those H's if the HA bond is polarized and the H seems positive. That bond between them has to be weak. The conjugate base has to be stable. And all three of those factors will affect the strength of an acid. Binary acids, which just means you have H with one other thing, if A comes from the same group, so let's say we're dealing with the halogens, HF, HCl, HI, so on and so forth, the strength of the bond is really important. The strength of the bond decreases as A becomes bigger because the H and the A, they're just farther apart. The bond strength decreases as you go down a group, so acidity increases. What that means is that HI is more likely to break apart than HF. And this is why HCl, HBr, and HI are much stronger than HF. HF is weak acid because it doesn't break down much. Bond polarity is also important here when A represents members of the same period. So now let's go across a row. Acidity increases as electronegativity of the element increases, because as the electronegativity increases, it's pulling more and more electrons toward it, leaving that H much more positive. So we know that happens as we go across. HF is much, much more electronegative than HN, for example. Let's continue our discussion of chemical structure and whether or not it behaves as an acid or a base. Well, we have something called an oxyacid, and that's where we have OH groups, maybe other oxygen atoms bound to a central atom. Do they act as acids, bases? Well, it really depends what's going on. If Y in my generic example here is a metal like sodium or magnesium, what happens is the O is very electronegative and it's pulling all the electrons toward it. So now O is super, super negative, which attracts that H to the O. So the O and the H hang out together as their own little ion, and we get a metal hydroxide, like sodium hydroxide or magnesium hydroxide. So these will break down into metal ions and hydroxide ions. Well, what if the Y is a non-metal? Well, now you've got O bonded to a non-metal, so you have a covalent bond, and they're not readily going to lose that OH. So it's either going to be acidic or neutral, but as the electronegativity of Y increases, so does its acidity. because you're going to be pulling those electrons more and more and more toward the Y, leaving that H on the end really, really positive, making it act more like an acid. What if there are other oxygen atoms bonded to the Y? Like maybe there's another O at the top or something. Well, they pull the electrons away from the OH bond, which increases polarity. And the strength of so now you've got an acid, because again, you're pulling all those electrons away and up away from that H, making that H very positive. The strength of the acid increases as the additional electronegative atoms are bonded to Y. So here's an example. HClO is weaker than HClO2, which is weaker than HClO3, which is weaker than HClO4. So the more oxygen atoms you add, the stronger the acid becomes. Or you could simply say in a series of oxyacids, as oxidation number on the central atom increases, acidity increases. One last consideration of chemical structure, and it's something called a carboxylic acid. The portion of the structure shown in red is the carboxylic acid group, or the carboxyl group. It's really hard to say. So what you have here is you have a C double bonded to an O, and then the C is also attached to an O and an H. A lot of students see that and think, oh, it's a base. That double bonded O is pulling all those electrons away, and that H becomes very, very, very positive, and it's that H that becomes the acidic H. And this is why vinegar is often written as CH3COOH, Chiku, as we always joke about, because you have CH3, and then that COOH group is just how you write it. But it's the H on the very end that is given away, not the H attached to the C. So I also have students who say, well, I don't understand why we don't write it CH4 or C2H4O2 or whatever, because we want to show which H is the one that is given away. So we write it in a particular way so we can show that acidic hydrogen. We mentioned these before, but let's just go over them again briefly. Up to this point, for the most part, we've talked about either Arrhenius acids and bases or Bronsted-Lowry acids and bases. Let's just review quickly the Lewis acids and bases. Kind of different. Now, in the other two models, it's the acid that's doing the donating. In Lewis, the acid is accepting the electron pair, and it's the base that's donating an electron pair. And a base can donate its pair of electrons to something other than a hydrogen. Here are some examples. BF3 is a Lewis acid, mainly because it has an incomplete octet. Remember, B can only make three bonds, so it just has 6 electrons around it. Fe3 plus ions also accept electron pairs donated from cyanide ions. Compounds with multiple bonds, like CO2, remember there's a double bond between the C and the O's. They will react with water to make carbonic acid. And then hydrated cations, like that hexaaqua iron 3 ion, will result from cations reacting with water. And as the cation's charge increases, they are more acidic. We'll take a look at this in depth, but let's look at the common ion effect on acids. I'm just going to tell you how I think of it. If you have HA breaking into H and A, what if there's already some A negative in solution? How does that affect HA? Well, if you think about this equation right here, this one right here, and think about Le Chatelier. If you already have some of that A negative, isn't it going to go in the reverse direction? Isn't it going to make more HA? In other words, HA is going to break down even less. So if there is already an ion in solution that is common to that equation, I'm not talking about some other element that has nothing to do with the equation. If you have an ion that has to do with that equation, it's going to force the reaction to go in the other direction, and HA is going to break down less. And this happens for both weak acids and weak bases. So the common ion effect is simply this. If you already have an ion that is common to that equation in solution, the HA or the HB is going to, that's not right, HB, whatever, the weak acid, weak base is going to break down less. That's what you need to know. It's not scientifically correct, but I like to think of it like this. There's already an ion in solution. There's no room for me to break down. Guess I have to stay together. In this unit, we're going to take another look at acid-base titrations. Why do we titrate? Either to find the concentration of one of the solutions or maybe to find the equilibrium constant for a reaction. Basically, what we have here is you've got a volume of an acid or a base, and up here in the burette, you have a known concentration of the opposite. So if this is an acid, up here is the base. And what you do is you do the titration until you reach the end point, which is either shown to us through a color change with an indicator or maybe using a pH meter and graphing it. And then from that information, we do math and we can find the concentration of our unknown acid. But titration curves are very, very important. By looking at the details and by looking at the shape, we can actually figure out what kind of reaction we have. Here is a graph for a titration with a strong acid and a strong base. Now, the first graph on the left is we started with a strong acid, we're adding the base from above. How do I know? Well, I started way low on the pH range. The graph on the right is the opposite. We're going to have a base down here, we're going to add acid. Notice the shape of the graph to the right. Initially, the pH is very, very low. And in between that initial pH and the equivalence point, the pH rises very, very slowly. And then when you reach the equivalence point, it just jumps straight up. You have that beautiful, almost vertical line there. The equivalence point means we have an equal number of moles of acid and base. And the pH in this case is 7 because the cation of the base and anion of the acid are not acids or bases and don't affect the pH. So when you have a strong acid and a strong base, the resulting equivalence point pH should be around 7. After that, the pH is going to jump up into the basic range, and that just depends upon how much excess base you add, what base you're dealing with. But if you titrate a strong acid and a strong base, you're looking for this very, very sharp S curve. It's very, very sharp. You're going to start really, really low on the pH or really, really high on the pH. And it's just a very clean looking curve. Now let's compare that to a weak acid with a strong base. So down here, weak acid. Up here, we're dripping in a strong base. The initial pH is not quite as low. You'll notice between the initial and the equivalence point, it's not quite as flat. It's rising a little bit faster than it did before. And if you want to find the pH, we need to find the concentrations of the weak acid and the conjugate base. We have to calculate pH of a buffer. It's just a little bit more of a complicated mess. But when you have a weak acid with a strong base, that resulting pH is going to be greater than 7. The base is going to win out, so to speak. After this, if you want to find out what the pH is, again, you're going to have to do some math, and we'll walk through it. But you really need to look at just how much excess base you have and then do some math. This is just a graph that lets you compare strong acids to weak acids each time we're adding in a strong base. So at the very bottom, you'll notice that is the curve for the strong acid. So it stays relatively pretty flat and then just jumps at that equivalence point. While the weaker the acids get, your starting pH is higher. You know, that first piece isn't quite so horizontal, and notice the equivalence point is much smaller. And the one thing you're not seeing in any of these graphs, but you see when we do it in the lab, is the S almost looks like somebody took the S and they pulled it and they kind of spread it out. So normally in the lab, you don't see that super vertical piece. It looks more like that. And that's the telltale sign that you've got a weak acid going on. And again, with weak acids, your pH at equivalence point is usually going to be much higher than 7. And lastly, let's talk about what a titration with a polyprotic acid is going to look like. Well, because they have more than one H, there's actually going to be a series of equivalence points. To be honest, when you do these in the lab, we don't always see a graph that looks like that. It's just kind of an ugly titration curve, and that's usually because those pKa values are so close together that instead of getting this series of hills, you just kind of get this ugly looking shape. But what you do need to do, so if you get a pretty graph like this, we can estimate the pKa values by looking at what we call the halfway point. That's the halfway point between the initial and the equivalence point. So for the first pKa value, you're going to look for the halfway point between 0 and 50, 25 milliliters. And what you do is you find that 25 milliliters, go over to the y-axis, and that pH would be the pKa value. Now for the other titration curve that's listed there, you'd have to go partway between 50 and 100. So you'd look at 75, go up, go over to the y-axis, and that would be your pKa value. And I'm sorry this one was so long, but I just felt like there was a lot we needed to unpack here, and then we'll work through the details in class.